Okay. So now, Asad, we need to do the second topic of materials, and that is basically solid material properties, right? It is solid material properties. First of all, Asad, what is a solid? How would you define a solid? G,
Um, a material which has compact particles.
which has compact particles, right? Apart from that, solid can also be, differentiated from a liquid on the basis of one important concept, and that is elasticity. And that is
Yes.
elasticity, right? Whenever you're talking about a solid, remember one characteristic feature of a solid that you apply some force on a solid, right? And after the removal of that force, the solid regain its original shape, right? After the removal of that force, the solid can regain its original shape. Does that make some sense?
Yes.
So this is how solids can be differentiated from the fluids. Apart from that, you've got many difference between the solids and liquids. Solids have, not solids are not that solids are more compact than liquids, right? Liquids do not have any particular shape. They get the shape of the container in which they are filled, blah blah blah. Okay. So the first
Yes.
topic in this subtopic is Hooke's law. How would you define Hooke's law?
Hooke's law, it
You know
says
what what
that
did what did the Hooke's law said?
the force is directly proportional to extension.
Exactly. Whenever you're talking about the Hooke's law, we need to remember one thing, that force is directly proportional. Whenever you're talking about the Hooke's law, force is directly proportional to the extension produced in a string within the elastic limit. Did you get that?
Yes.
Right? Force produced on a string, force applied on a string is directly proportional to the extension produced, but that has to be within the elastic limit. Elastic limit is the condition. For example, if I talk about a spring, you have got this spring, right, Assist? And
Yes.
that spring got some sort of mass at the end. Now, what we're going to do, we're applying some force in this direction, so you know that the spring would get extended like that, right? We've been applying force.
Yeah.
And as soon as we remove this force, the spring would ultimately come back and gradually the spring would regain its original shape, right? This one. Got it?
Yes.
So that is all due to elasticity. And we've just got to know that, the larger the amount of this force, the larger would be the amount of extension. Got it? But this has to be within
Yes.
the elastic limit. Elastic limit is a point where the body is not any more elastic, right? When the body would not be any more
Yeah.
elastic. So as per the Hooke's law, we can write it down in equation that force is directly proportional to delta x with a negative sign. Asad, what does this negative sign convey?
I don't remember.
Well, this negative sign is just due to the restoring force. This negative sign is just due to the restoring force. Got it? And what is the restoring force? Restoring force is a force which
What
pulls
do
the
you mean by rest
yeah, yeah, I've been just telling you. Restoring force is the force by which the force which pulls the object back to its original position when it has extended beyond limits, right? For example, you've got a mass over here, right? Asad?
Yeah.
Some sort of force would apply on this mass to pull it back to its original position. So that is the negative sign is for, right? F is proportional to delta x, yani force is directly proportional to extension, but with a negative sign. Is that clear?
Yes.
So we need to remember these two things, right? Force is proportional to the extension. And now if we remove this sign of proportionality, You remember that. You should remember that F is equal to minus
Yes.
kx, right? If we remove the sign of proportionality, we would be having a negative sign along with the proportionality constant. And this proportionality constant is known as a spring constant. Asad, what is a spring
Yes.
constant?
Um,
Everybody knows the formula, right? K would be equal to F upon X. This is what everybody knows. But what does the spring constant tells us about?
force per unit length.
Force per unit?
Length.
That is fine. Force per unit extension. That is what the spring constant is for. But the thing is,
Yeah.
what does
Sorry.
the spring constant really tells you about? It tells you about the stiffness of the spring. It tells you about the stiffness of the spring. So for example, you might have seen two kind of springs. There is a spring in your ballpoint, right? There is a spring in your
Yes.
pen, right? And then at the same time, there is a spring in the shocks of the car your dad used, right?
Yes.
Which we often call the shock absorbers. Can you tell me which springs out of these two springs would be more stiff? Gee, which spring
The
out
one
of
in
these two
car.
springs would be more stiffer? The one in the car, right?
Is it the one in the Yeah.
Exactly. So it has a greater spring constant as compared to the spring that you use in a pen. Got it? So whenever somebody is going to
Yeah.
ask you what is the spring constants, what does the spring constant tells us about, just tell him that spring constant is just the stiffness of the spring, right? How stiff that spring is. Got it?
Yes.
Okay. Now, the next important thing, we need to graphically analyze the Hooke's law, right? The second topic is some sort of graphical analysis of Hooke's law. I said since force and extension are directly proportional to one another, since force and extension are directly proportional to one another, what would be the shape of the graph between them?
A straight line through the origin.
Exactly. It would just be a straight line passing through the origin, right? And you
Mhm.
need to remember two things from this graph. This graph can tell you about two things. First one, if you're going to calculate the gradient or the slope of this curve, slopes of fx curve, it would always give you the spring constant. Got it? It would always give you the spring constant. Secondly, whenever you'll be calculating the area under the fx curve, what that thing gonna tell you? What would be the area
Um,
under the fx curve? Um, um, Asad,
the
it would be giving you the elastic potential energy stored in a spring,
Yes.
right? It would be giving
Yeah.
you the elastic potential energy stored in a spring. Now, for example, this is some sort of x and this is some sort of f. And I want you to calculate the elastic potential energy stored in the spring. So you'll be calculating this area, right?
Yes.
So how would you get me the area? G, how would you get me the area?
Um, half of F into change in X.
Exactly, half of f times change in x. Now you also remember one thing, that f is also equal to k times change in x, right? So k times change in x times change in x. So you can also write it 1 by 2 k change in x square, right? So
Yeah.
whenever you want to calculate the elastic potential energy for a spring which is within the elastic limit, you would either be using this formula or using this formula depending upon the variables given. Is that clear?
Yes.
And the fx curve would be, of many other ways as well. Now, for example, if fx curve is looking like that, you need to change the formula for the area. For example, if the f of x curve is looking like that, you need to change the formula for the area. This is easy. This is just a rectangle. But what you're going to do with this one, when the force is not uniform, how would you get the total area under this curve? When the force is not uniform, it is not a rectangle, it is not a triangle, it is not a square, not any of the shapes. So what you're going to do with it?
Not sure.
Well, remember, whenever anything in physics is variable, in this case, the force is variable, right? It can easily be seen in the graph. Whenever something is variable in the physics, you divide that variable thing into extremely small pieces to make it look like uniform. To make it look like uniform, right?
Uniform.
Okay. And what you'll do, you'll calculate the area under every part, and at the end of the day, you'll just add them up to get the total energy. Is that clear? So you can see
Yes.
that you have got innumerable uh, rectangles. You just need to calculate the area under these rectangles, and at the end of the day, just add them up. So the formula for this thingy would become summation f times delta x, where I starts from 1 and it goes up till n. So that is how we'll calculate the energy stored in a spring when the applied force is not uniform. Is that clear?
Yes.
Right? So this is what the Hooke's law talks about. The graphical analysis, you need to know the formulas, you need to know all this stuff as well. Any questions up till now, Asad?
No, not right now.
Okay. We'll get to the next topic now. And the next topic is just about we need to talk about some very simple terms. And these simple terms are stress, strain, and strain, and
Young's modulus.
Young's modulus. We need to know all these things. So first of all, what is the stress? How would you define stress?
Force per unit area.
Force per unit area, but that is the same thing as that of pressure, right? Pressure is also
Yes.
force per unit area. But you need to know the difference between the stress and the pressure. What is that difference, Asad?
G.
What is the difference between the stress and pressure?
Um, Not sure.
Well, remember, whenever you'll be talking about the stress is also the force acting per unit area, but this is force acting per unit area to cause deformation. To cause deformation. Is that
Definitely.
clear?
Yes.
And whenever you talk about pressure, the main purpose of the applying pressure is not to create the deformation. But in stress, whenever you apply some stress on an object, it would always be force acting per unit area to cause some sort of deformation. Okay? Deformation is
Yes.
the change in the shape of the object upon application of the force. Okay?
Yes.
And now, whenever you talk about the strain, what is strain?
Um,
Gee, how would you define strain? It
Rate
is the
of.
change in it is the change in length divided by the
Yes.
original length, right? So basically, whenever you're talking about the strain, remember, strain is of the just a measure of change in length due to applied stress. Is that clear? It is just the measure of the change in length
Yes.
due to applied stress. So that is how we talk about the stress and strain. Is that clear? Now the next thing that we'll be talking about is the Young's modulus. It is the Young's modulus. What is Young's modulus, Asit? Have you ever heard about it?
G.
Do you
The
want?
um
Did you?
the stress upon the strain.
The stress upon the strain, exactly. So Young modulus is basically, everybody knows that it is the stress divided by the strain, right? It is the stress divided by the strain. But Asad, on very logical terms, what does the Young's modulus refer to? What does the Young modulus tells us about?
The
It also tells us about the rigidity of the spring, how rigid your spring is. It tells us about the rigidity of the spring. The spring in the car, in the car, the shock absorbers in the car, and the spring that we're going to use over here would be having higher rigidity as compared to the one we use in the pen, right?
yes.
So Young modulus would always be stress divided by the strain.
Strain.
So now we just need to, open up the formula. So Young's modulus is stress, which is F upon A, divided by strain, which is the extension divided by the original length. We can also rewrite this formula to look like F times L divided by A times X, right? F times L divided by A times X. And most of the times we'll be talking about the spherical wire or a spherical spring, right? So this formula would automatically become Young modulus is equals to F times L divided by pi r square times X, right? Where pi r square is the area of the spherical wire we'll be talking about. Got it?
Yes.
So depending upon the variables given, we can calculate the Young modulus. Or else, if we have got the Young modulus, we've got the applied force, we've got the length of the wire, we've got the radius of the wire, we can also calculate the extension. Got it? So it is
Yes.
just about talk. It is just about the given variables, right? It is just about the given variables. We can easily calculate all these things. Is that clear, Asad?
Yes.
Yeah. The last topic of this chapter is basically the stress strain graph. Is basically the stress strain graph. The last topic of this chapter is basically stress strain graph. Now you got to know what the stress is and what the strain is. And if I draw a graph between the stress and strain, as Hooke's law stated, that stress is also proportional to the strain. So initially the graph between the stress and the strain would just be a straight line, right? Would just be a straight line. But then it would curve a bit and then it would curve like that, right?
Yes.
Just give me a second. Yeah, it would have a little bounce over here and then like that. Okay. So there are
Yes.
three, there are many points which needs to be considered. For example, the first point that we will be talking about is this point. Then we have got this point. Then we have got this point, and then this point. This is point A, this is B, this is C, this is D, and this is E. So we have got these 5 points which we need to talk about. GSS, do you know about the point A? What does it tells us about?
Um, is it the breaking strain?
No, not
I
really.
don't remember.
The object would break right over here. So it can never be the breaking strain. So the point A, remember, is known as a proportional limit.
Yes.
It is known as a proportional limit. So it is a limit of stress up to which, it is a limit of stress up to which stress and strain are directly proportional to each other. Did you get that?
G.
It is a limit of stress up to which stress and strain are directly proportional to. You can see that this is a perfect straight line, right? So if you talk about this first part of the curve, this is a point up till which the stress and strain are directly proportional to each other. So
Yes.
that is why we call it a proportional limit, right? And then comes the
Yes.
B. The point B is basically known as an elastic limit. We've been talking about this point even in the Hooke's law as well. What is elastic limit, Asad?
Um, a limit to which an object can be stretched.
Without permanent deformation, right?
Yeah.
Up till elastic limit, even after the removal of force, the body would regain its original shape, but not after the elastic limit. Did you get that?
Yeah.
So whenever you're talking about elastic limit, remember, it is a limit of stress after which the body will be permanently deformed. After which the body will be permanently deformed. Is that clear? So this is a
Yes.
point, and right after, as soon as the stress crosses this point, the body would be permanently deformed. Even after the removal of force, the body cannot go back to its original position. Got it, Ji?
G.
Now we need to talk about the point C. The point C is basically the yield stress. What is the yield stress, Asad?
Um, I'm not sure.
Remember, whenever you're talking about a yield point or the yield stress, it is just a point beyond which the material undergoes a sudden increase in extension as its atomic structure, right? As its atomic structure is significantly, you can call it reorganized. So it is a point after which the atomic, let me write it over here, after which the atomic structure of object organize, yeah, deorganize, right? There is a change in the lattice parameters of an object right after this yield point. It can either be over here or it can be over here. Did you get that? So whenever
Yes.
you're talking about a yield point, it is the point where the change in the atomic structure happens. Okay.
Yes.
Now we have got the point D. So whenever you're going to talk about the point D, it is the UTS. This point is known as UTS.
Ut-
And UTS is known as the ultimate, UTS is known as an ultimate tensile strength. It is known as the ultimate tensile strength. This is why we call it UTS. Got it, Ji?
Ye-
So UTS is the maximum stress that the solid can bear without cracking itself, right? It is the
Yeah.
maximum stress the solid can endure without rupturing. Is that clear? It is the
Yes.
maximum stress the solid can endure without rupturing. For example, whenever you want to buy some steel rods, the company would be telling you about the UTS. For example, if they tell you that the UTS of the steel rod is 10 megapascals, what does that mean? That as soon as you're going to apply 10 megapascals on the steel rod, the breakage of the steel rod is inevitable, whether it's going to break today or whether it's going to break right after a year, right? So UTS is the point that you need to consider whenever you're buying something like that, right? Whether there could be steel rods or anything that's going to support some structure. Did you get that?
G.
So UTS is the maximum stress, UTS is the maximum stress that an object can endure without breaking itself. So whenever you want to measure the strength of any solid, you need to check out its UTS, the ultimate tensile strength, right? And the last point, the point number D, the point number D is known as a fracture stress, right? Sorry, not D, it was E over here, yeah. So
E.
it was
Yes.
E. Now, what is E? It is the fracture stress. And what the fracture stress is? It is a stress at which the material breaks down, right? Such stress, yeah, such value stress at which the rupture takes place. Did you get that?
Yes.
So that is what you call the fracture stress, the point E on the curve. So these are the points that we need to know, Asad, on a fracture curve, right? तो ये सारी चीजें हमें पता होनी चाहिए. Clear है जी बात?
Yes.